All right, so we're talking about an infinite series. So we finished up with the 3/10 plus the 300 plus the 3,000. And we looked at how the partial sums were converging to a specific value of that. They converged to 1/3. So we knew that that series converged to 1/3. So that's great, but to have to look at each individual partial sum of a series to see if it converges is a lot of work for every series that we might do. And so we don't want to have to do that. We want to come up with some other rules for when a series may or may not converge. And so we're going to start with this first little rule here, which says if we have this infinite series, we know that it is possible for a series, for an infinite series to converge if the limit as k or n, because I'll use an n here, as k or n goes towards infinity of the kth or the nth term of the series approaches 0. Which, what does that mean? If the last term, if the limit of the last term approaches 0, that effectively means that I'm adding some stuff in here at a sub 1, I'm adding some stuff in here at a sub 2, and I'm adding some stuff in at a sub 3, and eventually down here at a sub n, I'm adding in such a tiny, insignificant thing that really what I'm adding in is nothing. And then all the terms beyond infinity, which, infinity goes forever, but the terms beyond infinity, or the terms at infinity, are insignificant. And so we're at 0 with them. And so I can take all of the terms before it and whatever their sum is, all the way up to that one that's 0, is just our sum. But if we look at the nth term or the kth term of a series, and as we approach infinity, it does not equal 0. That means that no matter how far on we go with this series, we are adding in significant pieces forever. Meaning that if I go towards infinity, I'm still adding something significant to this series, which means that it must diverge. Okay? So our first rule is going to be that if the limit as, I hate that I've used k here. So I'm going to use n pretty much the entire rest of this year. But if the limit as n approaches infinity of the nth term doesn't equal 0, the series is guaranteed to diverge. Okay? So what we're going to need to be able to do is write out a generic term or a generic representation of the series, and then look at the nth term, do the limit as the nth term goes towards infinity. Does that make sense? And then if that limit is not 0, it diverges. If that limit is 0, it is possible that this series might converge. We don't know for sure that it will converge, but it might converge. Good? Okay. So, and as we go through, we're going to eventually call this thing the nth term test for divergence. And we will note that in the nth term test for divergence, it only tells us divergence. It does not tell us if a series converges. It only tells us if a series diverges. Everybody sound good there? Everybody's good? Derek, how did your presentation go? Wonderful. That's great. All right. Are you laughing and crying at the same time? Oh, okay. That's bad. Okay. Justin, he's not laughing and crying at the same time like you were. I don't know. He was all about talking earlier about how he was laughing and crying. I didn't mean to insert a new page. Okay. I didn't mean to do that at all. Oh, wait, blank page. All right. So what we're going to start with here then is we're going to start with a geometric series. And we talked yesterday about, I said we're going to talk about sort of two different types of series. One is a geometric series. Then we're going to talk about power series, which oftentimes are geometric, but sometimes they're not. And then there's also arithmetic series. An arithmetic series, we're not going to deal with. An arithmetic series is just a series where there is a common difference between the terms, like 1 plus 3 plus 5 plus 7 plus 9 plus 11. That's an arithmetic series because the difference between each term is 2. Right? From 1 to 3 is 2. From 3 to 5 is 2. We're adding 2 each time for the next term. But a geometric series is a series, and these are the important ones. A geometric series is a series where there is a common ratio between the terms. So I take the first term, whatever it might be, I multiply it by some number. It could be 7, it could be negative 1/3, it could be pi, it could be 1/10, it could be anything. Okay? And then that's our next term. Then we multiply that second term by the same thing we multiplied by the first term, and then we get our third term. And we take that and we multiply by the same thing. We multiply by that 1/10 again. And then we multiply by that 1/10 again. And we multiply by that 1/10 again. Over and over and over again to get each successive term. That's a geometric series. We won't do anything with Kevin. We won't do anything with arithmetic series. There will be no testing on arithmetic series. It's not included on the AP test at all. There will be stuff on geometric series for sure. 100% stuff on geometric series. Hopefully, does that answer your question? Perfect. Okay, so yeah, we'll get to that. So we've written out this series as our first term, A, plus our second term, A times the common ratio, R, and then our next one is AR squared, because we're multiplying AR by R, and so on. So we've got A times R to the n-1, and the reason it says n-1 up there is because we started at an index of n equals 1. And so in order to get A as our first term, we need to have n-1 here, because that way, when we do n equals 1, that gives us R to the 0, which is 1, which means we didn't actually multiply that first A value by anything to get A as our first term. We could write it out as the sum from n equals 0 to infinity of A times R to the n. That would also be fine. Okay, so this would be acceptable too. That make sense? Okay. All right. You're gonna get used to it. I mean, we're gonna be using this notation over and over and over and over again. You'll get used to it. But we'll note that most of the time when we're dealing with geometric series, if we write out our sigma notation, if we write out our summation with an index of 1 to infinity, we're going to need to have an n-1 power in it. And if we write out our sigma notation with an index of 0, we're going to need to have a power of n just to get our correct series. Okay? So that's just kind of a thing that we're going to do. And we could start it at n equals 2 and then do AR to the n-2. We could start it at n equals 10 and we could do AR to the n-10. It doesn't really matter. The index and the power can shift and move up and down however you see fit. Just so long as you don't do it to get negative power. Good? Okay. All right, cool. So let's first start taking a look at some of the partial sums of this geometric series. Because what we're going to try and figure out is when does a geometric series converge and when does a geometric series diverge. And you may already know this, but we're gonna prove it right now. Okay. So first partial sum is A. Y'all agree with that? Second partial sum is, my internet connection is unstable. Can you guys still hear me in Zoom?
You dropped out for about 15 seconds there.
Okay. What was the last thing I said when I disappeared?
You were about to go over sorry, maybe it wasn't 15 seconds. You were just about to go over the partial sums, but whatever the first thing you said about the partial sums, we didn't hear.
Okay. Well, we're going to use the partial sums to help us figure out when this thing converges and when this thing diverges. For when any geometric series converges or diverges. So we're going to look at the partial sums. Our first partial sum is the first term, which is just A. That should be an easy one. Our second partial sum is just A times A plus R. A plus A times R. I think it's A times A plus R. A plus A times R. Our third partial sum should be A plus A times R plus A times R squared. Ignore how some of them are italicized and some are not. It means nothing. It's just how the equation editor does things for some reason. But what what can we do with this second partial sum here to rewrite it? Is there a way we could rewrite it? Okay, we could definitely take out a, right? So we could write this as a times a plus r. All right, what about this one? We could factor out, we couldn't factor out an r, right? Because we don't have an r in all the terms. We could factor an a out of it, right? We write this as a times, why did I write an a? That's a good question. A times 1 plus r squared. And what about this one? What? I did it with that one too. Oh, yeah, I don't know. Must be thrown off by that guy just walking around. Just walking back and forth. Man, no walk now. I don't know why. Okay. A times 1, we have the 1 this time. Right? A times 1 plus r squared plus r cubed. Good? Well, this seems all fun and good, sort of. Not really. It'd be cool if we could do something else with these. And I'm just gonna rewrite these in some certain way. I'm gonna start rewriting the first one in a certain way. And I want you guys to just bear with me for a second. Oh, somebody said something in the chat there. Yes, that's correct, Kevin. But how do we get to that? How do we get to this thing, Kevin? What's something in the chat? How do we get to this? We need to take the numerator here, because they're going to make these all fractions. We're going to multiply by 1 minus r, and we're going to divide them all by 1 minus r. And let's see what happens if we do this. Right? If I take a 1 minus r here and a 1 minus r here, what is that going to turn the numerator into? Yeah, it's going to be a times 1 minus r squared. True? What's going to happen over here with this one? That's not wrong. That's not wrong. Yeah, no, that's fine. Okay, all right, we're good. Okay, continuing on. What's the next one going to be? If I multiply this by 1 minus r over 1 minus r. Should become, what is this? Becomes 1. Right? So then we get a, what do we get? We get a minus r, and we get a plus r, and we get a plus r squared and a minus r squared, and we get a minus r cubed. Right? Over my a, 1 minus r. And what does the next one become? What do you think? Yeah, this one's going to become a times 1 minus r to the 4th over r. And we should probably note then that each of these partial sums is going to take on a form. The nth partial sum is going to take on the form a times 1 minus r to the n over 1 minus r. True? That look accurate-ish to you guys? People here that feel okay? Yeah? Okay. People at home, is that good?
Yes.
Yeah? Okay. Now, the first thing that we talked about with these partial sums was, well, the partial sum, if it is approaching, if the limit of those partial sums is approaching some value, then it should converge. Or that if the nth term is approaching 0, it might converge, and if it's not, it might diverge. So what we're going to do is we're going to look at the limit of this sum as n goes towards infinity and see what happens to this thing. And, okay, so any thoughts on how we might be able to figure that out? Right, but how are we going to figure that out? And there's going to be, we have these R values in here, which are a problem, right? Because R could be any ratio, right? So we, I got it, right? Okay, I have it here. Okay. I did have it here. Okay. No, we don't need to do a left and right limit. We need to deal with R in some way. So if we're looking at this limit as n approaches infinity of a times 1 minus r to the n over 1 minus r. Okay, not quite. What value of r is an issue here? Okay, an r value of 1 is an issue. Would you all agree that an r value of 1 is an issue? R equals 1. What happens if r equals 1? We end up with a 0 over a 0. Right? So we're gonna have to, we're gonna have to do something else there, and we'll look at that in a second. But what happens if r is positive 1, greater than positive 1, or less than, let's say, negative 1? Or greater than positive 1, right? See, what's going to happen there? If r gets, let's say r is bigger than 1. 1 minus r to the infinity, what's going to happen with this term in here? What? People at home also, you can answer the question also. Yeah, so if our r value is greater than 1, this number up here, we need to do this a little bit more rigorously. We can't just like take a guess. So how are we going to rigorously try and figure this out? Looking at the 4 of you here, looking at you at Zoom at home. I don't think anybody said anything in the chat. No, nobody said anything in the chat. You got to find a way to work out this limit. When r is 1, let's say when r is greater than 1, and when r is, we're just going to worry about positive values for this thing. R is greater than 0 or less than. Because there's going to be different things that go on here. Anybody have a way that they might see to work this limit out? All right, treat them as separate limits. In what way? What do you want to do with them to treat them as separate limits? That's a good idea. What separate limits are you wanting to look at? There we go. That's what I was looking for. Okay. So we're going to expand the numerator out here. This is going to give us a minus a r to the n over 1 minus r. And then we're going to be looking at 2 different limits. Okay? We're going to be able to look at a over 1 minus r minus a r to the n over 1 minus r. So let's write this. I'm not going to do page here now. We're going to have the limit as n approaches infinity of a over 1 minus r. And then we're going to have minus the limit as n approaches infinity of a r to the n over 1 minus r. Everybody good with that? Okay. First off, as n goes towards infinity, what is a over 1 minus r? No matter what r is, a over 1 minus r, if n goes towards infinity is just a over 1 minus r. So now we're looking at a over 1 minus r minus the limit as n approaches infinity of a r to the n over 1 minus r. And even here, we might now recognize that the issue is going to be between when r is greater than 1 and when r is less than 1 or greater than 0. Or if we're talking about negative values, basically, we're going to be concerned about when the absolute value of r is less than 1 or when the absolute value of r is greater than 1, just by looking at that second piece of that limit, right? That seems reasonable too. So how are we going to deal with that? When r is greater than 1, what is that going to tell us? Right. We're going to get, this is going to be approaching infinity, and the bottom 1 minus, r greater than 1, some negative number, but the power is going to increase more rapidly than this just linear piece in the denominator. And so this, if we look at this is we'll say this is infinity faster, this is infinity slow eventually, right, as r keeps getting larger and larger. Do y'all agree with that? Yeah, well, not even an infinity, it's just some number. Not even infinity, that's just some number, depending on what 1 minus r. So we're really looking at infinity over some number. And infinity over some number is just going to be infinite, which means that if r is greater than 1, this is going to diverge. But if r is less than 1, or in fact, if the absolute value, if we even think about the absolute value of r being greater than 1, if the absolute value of r is greater than 1, right, that means large negatives as well, right? Well, it doesn't matter. This would be then just a negative infinity, as n goes towards infinity. And then this would still just be some number. So really, the absolute value of r being greater than 1 is going to diverge. What about if the absolute value of r is less than 1? This is going to be, well, if we're looking at an r between -1 and 1, and I raise it to an infinite power, that's going to just be going to some number, right? Whether it's 0, right, if r is 0, or any other number besides 0, it's just going to be going towards a in the numerator. So we'll just have a over 1 minus whatever this small number is. Well, that small number is just some number. We have a over some number. A over some number is just some number. Right? And so really, this number is going to be smaller than what this is. And so this should then be approaching just 0. Okay? And so effectively then, our limit then approaches infinity for r value that is between -1 and 1. Should just be, let's say, for absolute value of r less than 1 should equal a over 1 minus r. And so we've effectively now said that a geometric series should converge, and it should converge to this value, a over 1 minus r, if the ratio is between -1 and 1. If the ratio is greater than 1 and the ratio is less than -1, it should diverge. What about if the r value is 1? Okay. Well, we end up with this a over this 1 minus r. We end up with this a over 1 minus r. With r equaling 1, those both are undefined. And so at r equals 1, it also clearly doesn't exist too. So really what we can say then is that a geometric series will converge if the ratio is between -1 and 1, non-inclusive. I think I have that on the next page. I do. Wonderful. Okay. So this is our geometric series, and it will converge if our a over 1 minus r value, absolute value of r is less than 1. It will diverge if the absolute value of r is greater than or equal to -1. Everybody good there? Or if a is 0. That's true. Or if a is 0. We're not going to deal with the case where a is 0. If a is 0, it will be 0. Series will just be 0 plus 0 plus 0 plus 0. That's true. And this thing down here, the convergence for -1 to 1, we call that the interval of convergence of the series. And the idea of the interval of convergence of a series is very important. We're going to talk much more about that as we move through this unit. The interval of convergence is just a set of values for which the series will converge. Everybody good there? Yeah, good. Very important to know that a geometric series converges for a over 1 minus to a over 1 minus r if the common ratio is between -1 and 1. Yeah. So let's take a look at these and see if we can figure out if each of these series converge or diverge. We're also, for this one, we're going to write it out as a, just a, write out the series like this one is. And for this one, we're going to write it out in the summation. So first off, let's write out this first series, just write out the terms, just to make sure that we can do that. Because I know the majority of you are not real well versed in series in general, because the school has never done a good job just teaching series as part of any class. How will we write this out? What's the first term? When n equals 1, what does this become? 3. And then when n equals 2, this should be 3/2. When n equals 3, this should be 3/4. We should probably be able to see n equals 4. This is going to become 3/8, and so on. Right? And I wrote 18. I don't know why I wrote 18. Because that guy is like that. Right. That guy is. And so on. All right. Now, next thing is, what is the common ratio of the terms? R is 1/2. The absolute value of R is less than 1, which should tell us that this converges. Whenever you say something converges, you need to give a reason why it converges. This converges because it's geometric and the absolute value of R is less than 1. Do the common ratio as a half. So it should converge to a value of A, where A is always the first term of this geometric series. In our case, that's 3 over 1 minus our R value, 1 minus a half. So 3 divided by a half is, so we should be able to say that this series is geometric with a common ratio of a half, which is less than 1 greater than -1. It converges, and it converges to 6. If I were to sum together these terms infinitely, we would get 6. Good? What about this second one here? This is the sum from n equals 1 to infinity of -1/2 to the n minus 1. Does that work for everybody? If I plug in 1, this is -1/2 to the 0, which is 1. If I plug in 2, this is -1/2 to the first, which is -1/2. If I plug in 3, it's -1/2 squared, which is 1/4, and so on. Okay? What is the R value? Our R value is -1/2. The absolute value of R is less than 1. Therefore, this series converges. What does it converge to? converges to A, our first value, which is 1, over 1 minus R. R was -1/2, so 1 minus -1/2. So we have 1 divided by 3/2. 1 divided by 3/2 is 2/3. Easy enough? Okay. Don't worry, I promise it's going to get considerably more difficult as we move through the unit. I know you're all very concerned. All right. Here's one that starts at k equals 0. That's fine. Is this a geometric series? Should we write out the terms? Let's write out the terms and see what it looks like. First term should be 3/5 to the power of 0, which is 1. Second term should be 3/5 to the first, which is just 3/5. Next one should be 9/25 and 27 125 and so on. Right? It does have a common ratio. It's definitely geometric. We're multiplying each successive term by 3/5. What is, what we just said is we're multiplying by 3/5. So the R value should be 3/5. Absolute value of R is less than 1. Tells us that it converges. And it converges to A, our first term. 1 over 1 minus 3/5. That'd be 2/5. 1 over 2/5 out of 80. Good? People at home, are you good? I don't have an unstable internet connection, do I?
Yes.
Yeah.
Okay, this should be pretty straightforward. I hope. Okay. All right, pi over 2 plus pi squared over 4 plus pi cubed over 8 plus dot, dot, dot. All right, so what can we write this as? The sum and n equals, let's do n equals 0. Just to do another one with n equals 0, since we did a couple of n equals 1. N equals 0 to infinity of 1. How can we write this out? Sure. Pi over 2 to the n plus 1. That'll work, right? That should do it, shouldn't it? If I started at n equals 0. We could have started at n equals 1, and then it would just been pi over 2 to the n. Right? That'd be fine too. Cool. All right. Pi over 2, pi squared over 4, pi cubed over 8, and so on. What is the common ratio? Pi over 2. Does this converge? No. Absolute value of R is greater than 1. This diverges. And same reasoning, I said always tell Y it converges. Well, if it diverges, also always tell Y it diverges. Good? Everybody here seems good. Everybody at home, are you all good?
Super.
That's good. Yep. Yeah, I mean, we're specifically right now, we are only talking about geometric series. That's the only type of series we've talked about. So yes, for now, that's good. If we were moving later on in the unit, when we've talked about some other series that are not necessarily geometric, you'll need to state, like, this is a geometric series. You can just write geometric series, absolute value are less than 1 converges. Just note that it's geometric if you're later on in the unit. You guys all hear that at home? For now, I don't need you to tell me it's geometric because that's all we're doing for now. But when we move on beyond geometric series, you'll need to tell me that it's geometric if you're using that reason. That it's geometric, and yeah, whether it converges or diverges, geometric, absolute value are less than 1. Correct. All right. Cool. Let's take a look at these ones. These ones look a little bit different. Yeah? Perhaps slightly more complicated. So, I said something at the beginning of the class today. I said something like, if you're looking at a series that is Starting at n equals 1, you need the powers to be in minus 1. Well, I don't have powers that are in minus 1, do I? I do not. No, that's a problem. So, what are we going to do with that? Factoring things out, what do you intend to factor out of that? Okay, yes. I half followed what you were saying. We're going to manipulate those exponents. Is that what you're saying? And then like pull some of the powers out of them and move them around. Yeah. That is exactly correct. So we want these to have, since this is n equals 1, to have a power of n minus 1, but 2 to the n minus 2 clearly does not, right? So what we can do is we can say, all right, let's make that n equals 1 to infinity. Let's just make it 2 to the n minus 1. Well, if I make it 2 to the n minus 1, I've gotten rid of one of those negative ones to the power, right? But exponent rules are convenient that I could, if I have the same base, I just add the exponents. So this could be 2 to the n minus 1 times 2 to the negative 1, right? 2 to the n minus 1 times 2 to the negative 1 is 2 to the n minus 2. I haven't fundamentally changed anything, but I have written it so that I have a 2 to the n minus 1. What can I do with these 3 to the negative n plus 1? How can I turn negative n plus 1 into n minus 1? Do what? I take out a negative. 3 to the negative n minus 1. Well, what does that mean? That means negative 3 to the negative 1 times n minus 1? Yeah. And, well, how can I rewrite that? What? How do I deal with 3 to the negative n minus 1? Yeah, we can just drop the negative 1 or negative. I don't need to write the 1 there, I guess. Right? It's 3 to negative n minus 1, so I can drop that to the bottom and make that a positive n minus 1 in the denominator. Everybody at home good with that? And here. And so at the same time as I do that, I'm going to drop that 2 to the negative 1 to the denominator as well. So I'm going to end up with 2 to the n minus 1 over 3 to the n minus 1, and then times a 2 down here. Everybody good with that? People at home good with that?
Yeah.
Yes.
Good. Okay, now what? I've got some pieces in the numerator that are to the n minus 1 and some pieces in the denominator that are to the n minus 1. So let's just make those all to the n minus 1. And I still have my 2 in the denominator. I have my 1/2. And then I have my 2/3 to the n minus 1. Everybody good there? And now this should be a geometric series. True? Let's write out the first couple of terms just to see what it looks like. If we put in n equals 1, what's our first term going to be? 1/2. Our next term, n equals 2 should be 1/2 times 2/3, which will be 1/3. The next term will be enough after this one. N equals 3 should give us 4/9 times 1/2, which is 2/9. And so, everybody good there? And we are multiplying each time by 2/3. So our common ratio is 2/3. Absolute value of r is less than 1. This converges, and it converges to our first term divided by 1 minus our common ratio. So 1/2 divided by 1/3. 1/2 divided by 1/3 is 3/2. Everybody here good with that? People at home good with that too?
Yep.
Wonderful. Excellent. Let's take a look at the next one. Man, walk down. Man, walk down. Walk down. Man, walk down. What's He's just walking around. What did he do? He's just walking around. Walking around. Next time, man, walk by window. I show you window. Okay, class? Okay, Zoom class. Okay. All right. Very strange. All right. What about this one? N equals 0 to infinity. What do we want these powers to be then? We want them to be to the power of n, not to the power of n minus 1 or 3n. We want, since it's n equals 0, we want the power to just be n. So let's see here. Negative 4 to the 3n. How can we rewrite that? Yeah, this should be the same as n equals 0 to infinity of negative 4 cubed to the n. Right? That's how exponent rules work, right? Just multiply 3 times the n, gives you the 3n, but we can expand it out the other way. What about 5 to the n minus 1? Right, so this is 5 to the n, 5 to the negative 1. We'll bring that 5 up into the numerator. Everybody good there? So we should be able to rewrite this. Should be able to rewrite this as the sum from n equals 0 to infinity of negative 4 cubed is negative 64, right? We have negative 64 fifths to the n, and we have a 5 up in the numerator. There's our series. And what can you tell me about this series? It is geometric. And what is the ratio? I wrote 16 instead of a 64, but yep. I think it's something about when I chopped off my fingers. Maybe my fingers don't. Nervous don't work right. I think it's a transmission from my brain. R equals negative 64 fifths. So what does that tell us? It tells us what? Converges. After the value of R is greater. Everybody at home good there? All right. I guess, I don't know. Yeah. You guys good? Nobody said anything.
I'm great.
Wonderful. 1 out of the 31 of you that decided to stay. All right. Now, let's take a look at this. This is where things get interesting. This is where things really get in. That's first stuff with the geometric series. Okay, that's cool. But this is where things really get interesting. So, could I, instead of writing this R, could I use X? Let's use X. Yeah? And let's write this out as a sum from n equals 0 to infinity of x to the n. That's what we're going to do. And that series will look like 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th and so on. Right? Well, our common ratio is x, isn't it? So if the absolute value of x is less than 1, or other words, if x is between negative 1 and 1, this should converge to a specific value for any x value between negative 1 and 1. You all agree with that? What should it converge to? It should converge to a over, we'll say 1 minus r, where r is equal to x and a is equal to 1. So this should converge to 1 over 1 minus x. In other words, suppose x was a half, and I did a half, if I did 1 plus a half squared, plus a half cubed, plus a half to the 4th, infinitely, that should be 1 over 1 minus a half. Should come out to be 2. Right? But that should work for every single value between negative 1 and 1, which is which is what we've been talking about. Which should be kind of, I don't know. It shouldn't seem that cool, but in a second, it might look more cool to you. Sorry, those of you moving my laptop around. Can you all still see me there?
Yeah.
Those of you here in the class can still see me. Okay. Here is our old friend, Desmos. Yes? All right. Here is 1 over 1 minus x. We're all familiar with this function, 1 over 1 minus x? Now, let's take a look. We just said that between -1 and 1, the series 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th and so on should look like this function. That's basically what we just said. True? So let's start putting in some terms. 1. I have to put y equals 1. All right. Does that look like the function with just one term? I put the first term, right? I put my first partial sum. Does that look like 1 over 1 minus x? Yeah, Jenna in the class is shaking her head tentatively. No, it doesn't, right? It definitely does not look like. Yeah. We're getting there. It doesn't really look like it. It looks exactly like it at 0, doesn't it? True? But that's the only place. All right. What about now? From -1 to 1. In fact, let's zoom in a little just so we can only sort of see -1 to 1. Not only, but well, let's zoom back out. At least at that one point, it's got the same slope. Right. It looks better, doesn't it? Would you agree? What about now? Yeah, it's got a closer slope at more points. It's looking more like -1 to 1, 1 over 1 minus x, right? What if I put another one? There's my next term. Looks even better. There's my next term. Looks even better, doesn't it? Yeah, I think it does. It looks better, right? I'm going to zoom back out, actually. Exactly. Let's go to our, let's put another one in. Looks even better, right? Slowly, it's getting better, right? Right, I'm going to get rid of all of this. I'm going to just do this. Root 5, right? That's what it looked like. What if I change that from 5 to like, let's zoom in a little bit. All right. Let's change it from 5 to, let's go to like 25. It's going to take a second here for the graphing calculator to fix it, but it did. There we go. It's looking pretty good there now. It's almost completely on that line, isn't it? With just 25 terms. Suppose I made that 50 terms. Computer's a little slow. Desmos it's got to do, all of these values all the way up to. That's correct. It should only match up till we get to -1. But isn't that cool? It is literally like, it is almost exactly the same here, all along here. Now, I'm going to let the computer do its thing. Everybody have patience. It's got to compute. That's what the computer has to do. It has to compute. And it's doing, there we go. That did it. Look at that. It's even better than the last time, isn't it? Okay. And it's going to keep getting better and better and better the larger the numbers that I put in are. I can't put in anything much bigger than like 100 or so because otherwise it just takes Desmos forever. But this series should perfectly match up with the function 1 over 1 minus x between -1 and 1 if I'm able to put an infinite number of terms into it. Okay. And given I put 90 terms in and it looks pretty darn good. Right? So you should be amazed at how cool that is. Isn't that cool? That if you write out 1 plus x squared plus x to the third plus x to the fourth plus x to the fifth, all the way up to x to the infinity, it should look exactly like 1 over 1 minus x. From -1 to 1. Pretty cool. It's cool. It's not the coolest thing ever. There'll be cooler things, but it's kind of cool. All right. Everybody good? People at home, are you good? Okay, somebody wasn't good. They left. Somebody was like, that's not good. I'm leaving. All right. You all good with that? Are you guys even there?
Good.
You're just like stunned in silence. Is that it? Okay. All right. So, did I finish talking about that? Yeah. Okay. I didn't say this bottom part. So, we call this thing a power series. Okay? So, when we take our geometric series and we put in this x value and look for the x values for which this series will converge and relate it to a function, we call this series a power series for 1 over 1 minus x. This is the power series for 1 over 1 minus x. And it's just this power series happens to just be a geometric series. And it happens to converge for -1 to 1, and it is centered at 0. This is the first series, power series, that you need to memorize. You need to know that the sum from n equals 0 to infinity of x to the n is equal to 1 over 1 minus x on the interval -1 to 1, non-inclusive. So you're going to need to memorize that. I'm going to give you a list of them eventually in the next couple of days that you need to have all of them memorized. Sound good? Okay. Cool. We can, very interestingly, we can take any power series and center it at any value that we want. We can also throw any constants into it that we want. Okay? So the power series centered at 0 will look like just x to the n times maybe some constant. Like if I throw a 2 in there, 2x to the n, that would look like 2 over 1 minus x. Okay? And that's fine. We can just put those 2's. We can just put those constants in if we want. But we can also write out a series to represent this same function centered at some other value. So ours was centered at 0. We centered it at 0. We went from -1 to 1. But if I wanted to center it at 7, I could just change the x value to x minus 7. And then it would be good for an interval 1 unit to the right and 1 unit to the left of 7. So it would be exactly correct on the interval from 6 to 8 if I replace the x with an x minus 7. We're going to do some problems with this eventually. Not today. That's the basic idea of it. That we can write out this power series with replacing the x with x minus a. And in fact, we're going to see that we can replace that x with pretty much anything we want. We can replace that x with a 2x if we want to. We can replace that x with a sine x if we want to, and it should still work. It's pretty cool. Yeah. Everybody good? Conceptually good? People at home on Zoom?
Yes.
Wonderful. Conceptually good people here. All right. Everybody ready to move to the next page? Okay. Let's see if we can find a power series then to represent 1 over 1 plus x. Instead of 1 over 1 minus x, we want 1 over 1 plus x. So, well, what did I just say? I just said that we could replace that x pretty much with anything we wanted to. What does 1 over 1 plus x look like? It looks like 1 over 1 minus what? Negative x, doesn't it? So in the form 1 over 1 minus x, what have I replaced the x with? I've just replaced it with a negative x. So in my series, all I have to do is replace the x to the n with negative x to the n. And usually if we have a negative in front of something to the n, we'll write it in this form. We'll say -1 to the n. You don't have to do that, but that's generally what we do because that helps us to note that we see that -1 to the n. We see that that series does what? It alternates. We call it alternating. It alternates. Everybody good there? People at the home Zoom place, are you good?
Yep.
Okay. Cool. So let's just take half a second here and see, Desmos should be able to tell us if we are correct. So everybody agree that that should be correct? It seems like that should be right. So let's take a look at what Desmos tells us. We want 1 over 1 plus x, and we want a sum from n equals 0. Let's just start it at 50, and let's say -1 to the n x to the n. And we'll give it a second there to try and figure itself out. There it is. Looks pretty darn good. Looks like we got the right thing. Centered at 0. From -1 to 1, looks like it matched up pretty darn well. Y'all agree with that? Isn't that cool? All we did is replace the x with the -x, and now we got a new function, right? And like I said, we should be able to do this with pretty much any function. All right. What if we wanted one for x over 1 plus x? Any thoughts on how we do that? All right, we need a to equal x, and we need r. That's good. A to equal x and r to equal -x. Okay. Effectively, all we've done is we've taken 1 over 1 plus x, and we've multiplied it by x. Okay. Cool thing about power series. That's fine. Just multiply your series by x. So what was our series for 1 over 1 plus x? It was n equals 0 to infinity of -1 to the n, x to the n. And then we said multiply it by x. All right, let's multiply it by x. That's fine, just put an x in there. Well, what does that turn that into? X to the same base. What do you do with the exponents? X to the n plus 1. So let's see if Desmos tells us that we are correct. So let's just throw in an x here. And let's just throw in an n plus, no, let me get that up in the numerator. N plus 1 up here. Did I reshare this? I didn't share it. So there's our x over 1 plus x, right? Our purple function has now changed. It's just slow because it's trying to calculate the other one while I was trying to graph x over 1 plus x. And then there's our summation one. And it sure looks like from -1 to 1, that is, again, pretty darn perfect. Would you guys agree with that? Pretty cool. You know, you want it to be 2x, put a 2 in there. 2x over 1 plus x. Right? You want it to be basically anything you want that you can put in this form. You should be able to do it. What do we got here? Let's see here. Yeah, okay. We're pretty much out of time. I think we'll probably stop there. And then we'll pick up and do some more with power series next time. I'm going to post up tonight a homework assignment. In fact, I'll post it up hopefully between this period and the next. If not, it'll be after school shortly. On geometric series, just the beginning of what we did. I will also post up the basic power series one. You may not quite be able to get through all of it. I mean, you could probably sort of like stumble your way through it, but we're going to do some more practice with the basic power series stuff tomorrow. So you should have a better clue how to finish that up tomorrow after the quiz. So we have a quiz tomorrow, Euler's method logistic growth, right at the beginning. It shouldn't take the whole period. I'm not going to make it too difficult or too long. I'd like to start you all off with a good grade, so I don't have any issues with people with grades this quarter because I just don't want to deal with it. Sound good to everybody? People at home, good? People here, good? That's all that's on the quiz, Euler's method and logistic growth. Yeah.